Thank you. Okay, so right, before we start, I just want to remind you, or maybe you didn't see this yet, I posted the next problem set on Canvas. So and the due date is next Friday at 11:59 p.m. Okay, this is because, give you a little extra time after class to work on it if you want. I just didn't want you necessarily having to rush to finish it by the end of class and then working through the lecture to turn it in on time. Okay, so there's one important caveat here. This is quite a bit longer than the first problem set. Right? It's 5 problems, and they're divided into 11 parts total. Right? So I am only requiring you to pick 4 problems to be graded. And if you submit 5 correct solutions, you'll just get extra credit for the 5th ungraded problem. I'll grade that separately and just add that to your least score problem set after dropping 1 problem set. Right? And that's in the syllabus, right? I'll drop the lowest problem set. After that, if you decide to do the extra credit, then I'll add additional points onto your lowest problem set score after the dropping. Okay? Pick 4 problems to be graded, and let's just say submit a 5th, or I should say the 5th, for extra credit, if you so choose. Of course, you don't have to do that. Okay? Right, so everybody who turned in their problem sets digitally has already looked at the comments that I gave them. But everybody else, I just handed your work back. If you think anything is unfairly graded or I missed something that you wrote, just let me know. We can talk it out, and if I'm wrong all the time. So if I'm wrong this time, let me know. Okay? Okay, good. So let's see, where were we? We just finished on Tuesday. Well, not quite finished. We came up with this notion of a metric relating to the stereographic projection, right? Wherein, amazingly, we were able to make sense of what it means to compute the distance between the number infinity in the extended complex numbers to any other complex number, right? So, I just want to make a few more comments about that before we move on. Okay? So, remember, we had this picture. Here's our Riemann sphere, and here's our point, the North Pole, right? And I said, well, on the Riemann sphere, it makes good physical intuitive sense to define a neighborhood of this point N, right? It's just a cap on the sphere. So that is to say, once we come up with the notion that this metric chi, right, this metric that we defined last time, is in fact a metric. It behaves like the Euclidean distance. We can express this cap in terms of chi, right? This is to say chi of z to infinity. Remember, chi takes inputs complex numbers or extended complex numbers. So this is a lowercase z, right? This is actually a complex number, not its stereographic projection. Out of context, you can't tell the difference between a lowercase z and an uppercase z. So this neighborhood is described by chi of z comma infinity being less than rho for some real number rho, right? Which, if you think of chi as like the normal Euclidean distance, this is just like having absolute value bars or modulus bars around z minus infinity, right? Because it's a metric, it behaves the same way as the usual Euclidean function for distance. Okay, so that is to say, the expression for a neighborhood of infinity is exactly the same in this metric, chi, right? We have the metric of the difference of 2 points is less than some fixed real number. Okay, so that is to say, this expression, this inequality, chi of z comma infinity is less than rho. What should I say here? I should say, of course, with rho less than 2, or actually I guess I should say less than or equal to 2. Why do I insist that rho is less than or equal to 2?
Because of the radius of the sphere.
Exactly, because the Riemann sphere has radius 1, or diameter 2. Here's our point, 0, 0, 0, and this distance is 1, right? So the largest neighborhood of the point n, or i.e. the point that stereographically projects from infinity to the Riemann sphere, n, the largest neighborhood we can come up with is the entire sphere, right? All the points that are at most 2 away from it in free space that lie on the sphere. Okay. So this neighborhood on the sphere is the projection of all points in the complex plane lying outside a circle. Right? We already made geometric sense of this, but remember at the end of last time we derived a formula for what this means, right? An algebraic way of computing this. So this condition expressed in terms of the complex number z is just 2 divided by the square root of 1 plus the modulus of z squared is less than rho. And this is true if and only if. Basically what I want to do here is solve for the modulus of z, this inequality, if and only if I get the square root of 4 over rho squared minus 1 is strictly less than the modulus of z, right? the equation of a circle of radius rho, and I'm saying that z has to lie outside that. Okay, this matches our geometric interpretation. Okay? So, good. So that pretty much marks the end of chapter 1. Okay? Everything we've done up to now is just essentially the basic geometry and topology, we've even touched on a little bit, of the complex numbers. That might seem like overkill that we spent 3.5 weeks doing this. But I have to tell you that when I was a sophomore in high school, I had a really good pre-calculus teacher that touched on most of these things. And that's essentially why I became a math instructor. So this is really important to me personally. And I think that because we spent so much time here, you'll have an easier time interpreting all the results that we now develop related to calculus of a function of a complex variable with complex output. Okay? So, much credit to Sherry Osterheld. She inspired me to become a mathematician. So I try to imbue whatever I do in terms of instruction in her spirit. And that's why we spent so much time on chapter 1. Okay. So now, hopefully we have a very concrete idea of how to work with complex numbers geometrically and algebraically. Now we can move into starting to try to develop calculus, essentially. What it means for a function of a complex variable to be differentiable. And surprisingly, or maybe it's not so surprising since I've spent so much time building up to this, the notion is quite different from what the notion of differentiability is for functions of a real variable. But formally, the basic definitions look kind of the same. So we're going to start at the baseline. We're going to talk about we're going to start just talking about what a function of a complex variable actually is. Then we'll talk about limits and continuity. Right? This is a similar pathway that you may be familiar with from Calculus 1. Right? And then we'll get to the notion of complex differentiability, which is known as analyticity. Okay? Because, well, there's lots of reasons why we use a separate word. We'll get to that. For now, let's just talk about, let's start by talking about what complex functions are. Okay? So, what we mean, the object of study at hand, is some function which takes c to c, or more generally, if u is some subset of c, we may well study functions that take u to c. We can restrict the domain, and everything in our development will behave essentially the same, right, when we look at some subset of the complex numbers. Okay? So, is our main object of study. Okay, and just notationally, we often write W is equal to f of z, right? The output of a complex function will typically denote W. This is just convention that makes it easy for us to know what we'd be on the same page at all times. Okay? So, just as any complex number, any fixed complex number can be written in terms of its components, its real and imaginary parts, so can a function be written in terms of its real and imaginary parts. Right? So z has, our input has real imaginary parts, say x and y, and w, our output, has real and imaginary parts that depend on both the real and imaginary parts of z, both x and y. Okay? So let's say if we stick with our convention that we've been using so far, that z is equal to x plus iy, then we may write w is equal to, well, let me just be totally explicit here, f of x plus iy is equal to some real function, some function of two variables, u of x comma y, that has a real output, plus I times v of x comma y, another function of two variables that has a real output. Okay? So, basically what I'm saying here is that a complex function of a complex variable is essentially characterized by two real functions of two variables. Okay? So a complex function of a complex variable is essentially two real functions both of two variables. Okay, so let me just give you some examples here. So let's note for example, the function f going from c to c, given as f of z is equal to z squared minus 1 divided by z squared plus 1 is not defined at z equals plus or minus 1, right? That is to say, our denominator becomes 0, despite the fantastical properties of the complex numbers, we still can't divide by 0. Unless, of course, we're in the extended complex numbers. We'll talk about that later today. But when I'm just considering C, I'm not defined at plus or minus 1.
Yeah.
Why would that not be defined? Is c squared plus 1 in the denominator?
Oh, I'm sorry. I reversed my signs here. Okay. Yeah. Thank you. That makes way more sense, right? What I wrote first makes no sense. Right, so the denominator goes to 0 here at plus or minus 1. So we're not defined. So we say the domain of definition of F is the complex numbers minus the set 0, 1. Okay, I'm throwing some notation here at you. This slash, anybody familiar with this? Okay, this is set minus. It's the set of all complex numbers minus the set on the right. Just the set consisting of 2 elements plus and minus 1. Okay, so right. So in other words, what I'm saying here is technically this is not correct because I wrote C as my domain. Right? So really what I want to write is and F maps C minus the set plus and minus 1 goes into C. Okay? Confusing point. Remember when we were back in section 1.6, we made a definition of what a domain is in terms of a characterization of a type of planar set. Right? A domain is an open and connected subset of the complex plane. That is distinct from this word here, domain of definition, which is really annoying, but you'll see this everywhere in complex analysis textbooks, right? So let me write this down. A domain of definition need not be a domain in the sense of being an open, connected
Bless you.
set, subset I should say, of C. Now, I should point out, in this case, for this function f I have defined, its domain of definition is C minus plus and minus 1. Is that a domain? What do we think? Is C minus plus and minus 1 a domain? Okay, I see a head nod. Yes, it is. Okay, let's look at the picture here.
Is the point considered its own boundary?
Is a point considered its own boundary? So, if you look at a set that's a single point, if you take any neighborhood around that point, then you must contain a point in that set, i.e. the point itself, and a point which is not in that set, anything around it. So yes.
It is a domain.
So say again.
It is, there's a C minus, plus or minus 1.
Is a domain. Yeah, exactly. So here's, I'll put empty circles for a set not included, or a point not included in our set. -1 and 1. And I include everything else in the complex plane, right? That is to say, for any point, any other point I pick that's in this, right? Say, here is some point in C minus plus or minus 1. I can put an open neighborhood. Again, I broke my convention here. This should be a dashed line. I can put an open ball around this point, which does not intersect the points that, or include the points that are not included in my set. So it's open, right? And it's also connected, right? So any other point here, I can connect by a polygonal path. And I wouldn't ask you to make a precise argument for that, except for whatever's on the homework. Problem set 2, right? There's some potentially precise things I want you to say about topology. But yeah, you should be able to basically reason about what's a domain and what's not. Okay, so in this example, my domain of definition happens to be a domain in the topological sense.
Yeah, just a quick question about the homework.
Yeah.
If we do all 5 problems, do we have to know which ones we want graded?
Yeah.
Or will you just take the one we get the worst points on?
I would prefer if you just told me which ones you want graded. Yeah, that would be less ambiguous, right? Okay, good. Okay, so here we've concluded the domain of definition of F is a domain. Okay, what's an example of a, sorry, did you have a question?
I was gonna ask about domain of definition to different domain.
Yeah, good. So I was going to ask you all the same thing. Can you construct a function whose domain of definition is not a domain in the topological sense? Yeah.
The complex numbers minus the set of the modulus of z is less than or equal to 1. So the circle at the center is cut out from the complex numbers.
So you're saying we'll cut out the unit disk
Yeah.
from the complex numbers.
Still open and connected, right?
That's still open and connected.
Would it be open if you...
You said less than or equal to, right? And we're taking the complement of that, which means...
Right, okay, so just less than?
Right, so that's not open.
Okay.
And this is something I ask you to prove on the current problem set. Show that a set is open if and only if its complement is closed. This is the way that we make precise how open and closed are opposites. You look at the complement of one. The complement of an open set is a closed set, and vice versa. Yeah, good. So certainly we want to consider functions with domain of definition. A closed set, which precludes the domain of definition being a domain, right? Because a closed set is not open, unless, of course, it's either all the complex numbers or the empty set. Okay, those are the only sets in C that are both open and closed. I quoted you that result, I think on Tuesday, maybe last Friday. Good, so that's one example, right? We could take f a function. So I'm going to write down a less exotic example than what you said. We could take a function f that goes from the closed unit disk into C, right? So that is to say, such that Z is less than or equal to 1. This has domain of definition, which is not a domain. Okay, so that's one way we can fail to be a domain. Can anybody construct a function? Yeah.
You could have C minus, or C cut out so like all complex numbers with a modulus between 1 and 2.
Yeah, you could cut out an annulus from the plane.
And then if you do not include 2 and like 1 and 2 with the definition, then it would be open but not connected, right?
Yeah, so depending on if you include the boundary of the annulus, you can make the complement open or closed, whatever you would like to do. So yeah, let me take the extreme version of that example and make my annulus infinitely thin. That is to say, I can write a formula for a function f. So if we let f of z be given by the formula z squared plus 1 divided by the modulus of z minus 1 then f has domain of definition. I'll draw a picture for this. Remember, this is our main example. What we gave as an example of an open but not connected set, right? I'm missing the circle of radius 1. That is to say, this function divides by 0 for every complex number that has modulus 1, i.e., we're missing this whole unit circle. Right? This is a special case of the example that you were describing, right? Okay? Which is open, but not connected. Okay? So you can define a function on any subset of the complex plane, and where it's defined is the domain of definition. Okay, which is, I hope we now realize, not necessarily coinciding with our topological definition of domain. It's really unfortunate that these terms coincide. But again, there are certain things that we're just stuck with because of history. I found a really cool website right before I came to class today about the history of a lot of terms in mathematics. I'm definitely going to lift some material from that to talk about what analytic means when we talk about that next week. But maybe I'll just send that out over Canvas after class. You might find some interesting things. Maybe you can look up some mystifying terms from some of your other math classes that you've taken. Okay? So, good. Right. Okay, so just a quick example. I'm going to ask you to find u of x and, u of xy and b of xy representing f of z given as z squared plus 2z. Okay, so in other words, I'm looking for the explicit decomposition of this complex function of a complex variable into two real functions of two real variables. How do I proceed here?
Plug x plus yi into the z squared plus 2z.
Yeah, that's exactly what I want to do. I just want to say z is equal to x plus iy and plug it into this formula and then collect terms that don't have an I and collect terms that do have an I factor. Okay, so we'll just let z equal x plus iy. Then f of z is equal to x plus iy squared plus 2x plus iy. Okay, I do some multiplication and collection here. What do I get? I get x squared plus 2ixy minus y squared plus 2x plus 2iy, or rearranged, what do I get? I get x squared, minus y squared plus 2x plus I times 2xy plus 2y. Okay, so all together I get uxy is equal to my first real part of my output, x squared minus y squared plus 2x, and v of xy is just equal to 2xy plus 2y. Yeah.
Depending on the form of f of z, will there always be a decomposition to two functions?
Yeah. So
For any? Okay.
yeah, this a complex function of a complex variable is equivalent to two functions of two real variables.
And those two functions of real variables are always be able to, or are always findable through algebra.
I didn't say that.
Yeah. Okay.
All I said was that a representation
Could exist.
exists. Writing it down might be quite the challenge, or perhaps even impossible. We'll talk about a lot more about that as we begin to talk more about analyticity. Okay? And actually, the functions that we want to consider when we try to start to do calculus. Okay? Good. Okay, so right away, why did the development of calculus happen so rapidly for functions of a single real variable with a real output? It's because, in part, you can graph them. You can easily make an image that represents how a function behaves. Not so for complex functions of a complex variable. Because of this fact that a complex function of a complex variable depends on two real functions of two variables, two real variables. So we would need 4 dimensions to draw the graph of a complex function of a complex variable. Okay? So that is to say, graphing complex functions is, in general, impossible. disappointing. But what we can do as an alternative to this is compare what the domain of definition looks like in the complex plane with what the image looks like in the W plane, right? Again, going back to this convention, but when we set W equal to f of z, we can compare the domain of definition in the z-plane, right, a copy of the complex plane depending on my input, with the image in the W plane, a copy of the complex plane depending on my output. Okay, so perhaps not as nice as making a graph, but still holding a lot of information for what the function f does.
Is this kind of like what we do in linear algebra when you look at like the way vectors transform?
So, yeah, it's the same notion of image. Exactly. Right? And in linear algebra, you're even worse off, right? Because you're working in functions that go from m dimensions to n dimensions, right? So, you have even less chance of being able to make a meaningful drawing. Like, you know, if your output vectors are 4 vectors, what are you going to do? Not much. You know, maybe look at level sets of your image. But yeah, so we're worse off in complex variables than working with real variables, but we're not as bad off as in linear algebra. Okay, good. So let's do some examples of this process. Okay. Okay, so let's describe. Oh, I should say to that point, you know, so in a certain sense, yeah, we're worse off in linear algebra, except for the fact in linear algebra we're only considering functions that are representable by matrices. In complex analysis, we're considering arbitrary functions, not necessarily representable by a matrix. So there's trade-offs. Okay. So, and you'll see what I mean. Here. Describe the image of the function f of x is equal to, I'm sorry, f of z, sorry. F of z is equal to x squared plus 2i. So, okay, I always make this point to my calculus 1 students. A formula alone is not enough to specify a function. You have to specify its domain of definition. Right? So I haven't told you that yet. So describe the image of the function f of z is equal to x squared plus 2i. defined on the closed unit disk. Modulus of z less than or equal to 1. Okay, I told you we would be concerned with functions defined on closed sets, and here, for example, is 1. Okay, so really what I'm asking for is here's my z-plane. Okay, I act on this copy of the complex plane by the function f. I get over here my w-plane. And let's analyze what this function does. First of all, let's decompose it into two real functions of two variables. What is the real part of the output of f of z?
X squared.
It's just x squared, right? So u of x comma y is just x squared. It doesn't it happens to not depend on y at all. Okay? So furthermore, the imaginary component function v of x comma y is what?
It's 2.
Is 2. Yes. Good. Constant function. It doesn't depend on x or y. I mean, you know, it's vacuous to say that this is a function of two variables, but we still can say it, right? Okay. So, as we plug in points here, when I square x, what is my range of possibility for x squared? For any complex point I plug in to f. What's my range of the real value of the output, f of z?
0 to 1.
0 to 1, yeah, good. And as I plug in any complex point to f, what's the range of my output for my complex component?
2.
It's just 2. Yeah. So what I get is the line segment from 0 to 1 at height 2. Okay. So if you want to think of this kind of geometrically, we're taking this whole disk and squishing it into a closed interval and shifting it up to this point. Okay? So let me just emphasize, here's our domain of definition, which in this case is not a domain in the topological sense. And here's our image. Okay, kind of worried, I forget. In the textbook they might say range here, but I like to reserve the term range for the possible things that are hit by the function, and the image is the things that actually get hit by the function. Right? So that is to say, the range of this function f is all the complex numbers, and the image is just exactly where it lands, this closed interval at y equals 2, or I'm sorry, v equals 2. Just for consistency, here's my x and y axis, and my output w has axes u and v, the way I've been writing it, right? for some ambiguity here versus, from what I say versus the textbook. It might say range when it means image. Sorry about that. Okay. And the reason that I insist on using my own convention is because that's a more modern convention, right? If you pick up a random textbook published in the last 40 to 50 years, you'll see, on average, something more consistent with this terminology, image. Okay? But if you look at an older textbook, you might see range, meaning image. Very confusing. This is why I thought that website I found today was so interesting. Why do mathematicians choose the terms they choose for different concepts, especially when they choose the same term? Yeah?
Something in all my classes this semester that changes is what image and range and codomain all mean.
Right. Okay. So yeah, codomain and range are synonymous to me.
Okay.
Target space, also synonymous.
Yeah.
Target space, range, and codomain.
An image is reserved explicitly for what the function maps to.
The values that the function takes. Yeah, exactly.
Takes or outputs?
Sorry, not takes in,
yeah.
but the values that
Okay.
the function achieves.
Yeah, sure.
Say. Yeah. Yeah. Okay, let's continue with some examples here of sketching domains of definition versus images. Okay. 2, let's say sketch the image of f of z equals z cubed with domain specified by the modulus of z is less than or equal to 2, and the imaginary part of z is greater than or equal to 0.
That's the domain of definition.
This is the domain of definition.
Okay.
All this together. Okay? So it's a half disk, right? A closed half disk, right? We include all our points on the boundary of the disk of radius 2, and then we cut off everything that has imaginary part less than 0. Okay, so anytime I ask you to sketch the image, it's probably a good idea to first sketch the domain, if you can. Okay, so okay, here's 2, here's negative 2. Okay, here's my z-plane, x-axis, y-axis, and this is my domain of definition. Okay, so what happens when we evaluate all these points in the domain of definition by f? The w-plane, here I have my u-axis and my v-axis. Now, I could, of course, try to write my function f in terms of real valued component functions, u of xy and v of xy. But let's try to be a little more clever and do something that takes less computational work. Okay? So notice that in my domain of definition, I have this point. right? This point, which is, or rather, this whole line of points, which has capital arg, let's see, is equal to 2 pi over 3. Okay? So, what do I know about a complex number with argument 2 pi over 3?
If you cube it, it has a new argument of 2 pi or 0.
Yeah, exactly. For the value at 1, right? This is a cube root of unity on this line. So I cover everything in the unit disk by the image of this point, right? So, and when I go all the way out to 2, I have to cube the modulus as well, right? So what I'm saying is that this part of the domain of definition alone already covers the disk of radius 8. Okay, so that tells me what happens for all the points here. How about this remaining chunk of my domain of definition?
Just like overlaps back onto itself.
Yeah, right. Notice that this remaining chunk is half of the next interval to the next cube root of unity. Yeah? So that means we cover the top half of the disk of radius 8 again with just this remaining wedge of our domain of definition. Okay, so it's kind of making some impromptu notation here. This is saying that, okay, I cover the disk of radius 8 once, and then I cover the upper half of that disk twice in this entire domain of definition. Does that make sense?
Could you look at like the way we looked at the argument as like that branching shape thing?
Yeah, so we'll talk about that in great depth in the future. But yes, somehow the image has more than one sheet. We're kind of layered on top of one another here. We'll talk about that more later. But for now, let's just make this impromptu convention to say that it's covered more than once in the upper half.
So it is relevant to show that it's covered more than once.
Yeah. We want to keep track of that information somehow, even if we don't have a formal treatment of what that means topologically or in terms of being differentiable or not. Okay, but yes, we should come up with some way to keep track of that. That's why I just make this convention offhand. Well, really, the textbook does it, but I'll stick with it. Okay, good. Okay, so let's see. Here's a definition you've probably seen before. And it's exactly the same as it is for any type of function we may want to consider. But I'll say it again anyway, because it's worth noting. A function is called one-to-one or injective if f of z1 is equal to f of z2 implies that z1 is equal to z2. Okay? So in other words, this last function we described is not injective, right? Because this point here maps to the same point as this point here, right? That's this second covering of the upper half disk. Right? So this example is not injective. Okay, again, I don't think the textbook introduces the term injective, but this is what you'll see everywhere. You'll also see one-to-one fairly commonly, but we'll use both interchangeably, just because I want to instill in you the broadest mathematical culture that you can attain, right? Just so you can pick up anything and interpret it with the least confusion. Okay? It's kind of a sacrifice. We take the confusion now where we can talk about it together, so that when you're out in the world alone, you can do your best at interpreting whatever you happen to come across. Okay? Some people disagree with that philosophy. If you have a problem with it, let me know. Okay. So let's look at an example of a function which is injective. So let's define f of c is equal to 1 over z, the inversion mapping. Okay, quick question. What's the domain of definition of this function?
All complex numbers that are non-zero.
Complex numbers which are not equal to 0. Yes, correct. However, it will be convenient for us to be evaluating this on the point 0. So instead of looking at this as a function from c to c, we'll look at it as a function from c hat to c hat, the extended complex numbers, and define f evaluated at 0 to be the point infinity, and f evaluated at infinity to be the point 0. We haven't discussed limits yet, but this kind of matches what we think. If we have something infinitely large in the denominator, it tends towards 0. As the denominator grows in modulus, we tend toward 0, right? And as our denominator tends towards 0 in modulus, we get infinitely large, right? So we define from c hat to c hat. So this is my full domain of definition, c hat, where 0 equals infinity, and f of infinity is equal to 0. Okay. Is 1 to 1. Okay, why is this? Well, every complex number has a unique inverse, right? So that is to say, if I have two complex numbers, z1 and z2, with the same inverse, that means that z1 equals z2, right? Okay. So, it's not just for convenience that I make the domain of definition for this function, and its range, the extended complex numbers. In fact, the image of this thing is the complex numbers, the extended complex numbers, right? I hit everything. It's not just for convenience. There's a natural geometric interpretation on the Riemann sphere of the inversion mapping. Okay? So let's see what that is. The inversion mapping. Which we'll define as W is equal to 1 over Z. Corresponds to rotation of the Riemann sphere by pi radians about the x1 axis. Remember, when we consider the Riemann sphere, we use the coordinates x1, x2, x3, just so we don't confuse ourselves with x, y, and z representing our standard complex number, z equals x plus y, I, y, right? Okay, so in the problem set that I just sent out before class today, I asked you to come up with a geometric argument for this, which I think is actually a pretty fun exercise. And once you see it, it's really cool. But again, as has been the trend recently, we'll just do some algebra together, and then you'll convince me that you understand the geometry. Okay? Okay,
Does
so
it have something to do with the fact that taking the reciprocal of a complex number is the same thing as dividing by its square modulus, and
you'll tell me this when you write it down. I'm not saying you're on the wrong track, but think about it. Okay, so let's take our stereographic projections. X1, X2, X3, the projection of Z, little z, and capital W equal to Y1, Y2, Y3, the projection of little w, which remember is we define to be 1 over z. Yeah. Then, just by our formulae for going from a complex number to a point on the Riemann sphere, let's compute. So x1 is equal to 2 times the real part of z. And these are the formulae we derived last week. Yeah. Divided by the modulus of z squared plus 1. x2 is equal to 2 times the imaginary part of z divided by the modulus of z squared plus 1. And x3 equal to the modulus squared of z minus 1 divided by the modulus of z squared plus 1. And similarly, we have y1 is equal to 2 times the real part of 1 over z, right? Because I'm letting w be 1 over z, divided by the modulus of 1 over z squared plus 1. y2 being the 2 times the imaginary part of 1 over z divided by the modulus of 1 over z squared plus 1. And y3 being equal to the modulus of 1 over z, modulus squared minus 1 divided by the modulus of 1 over z squared plus 1. Okay, so now I want you to recall that the real part of 1 over z is equal to the real part of z divided by the modulus of z squared. Does that look familiar? Okay. And the imaginary part of 1 over z is equal to negative the imaginary part of z divided by the modulus of z squared. So now what I'll do is just plug these formulae into my formula for y1, y2, and y3. Okay, so these facts together imply that y1 is equal to 2 times the real part of z divided by the modulus of 1 over z squared plus 1 times the modulus of z squared, right? I've just substituted in the real part of, for the real part of 1 over z, the formula that I just wrote, okay? Which just gets me back to my original formula for x1, right? I just get 1 plus the modulus of z squared, which is just x1. Okay. What do I get for y2? I get negative 2, the imaginary part of z, divided by the modulus of 1 over z squared, plus 1 times the modulus of z squared. So I get negative 2 times the imaginary part of z, divided by 1 plus the the modulus of z squared, which is just negative x2, and I've just picked up a negative sign here. Okay, and then for y3, what I get is, well, there's no substitution here. Really what I'm doing is, what I'll do is multiply by a fancy version of 1, right? This is an equivalent expression, right? As long as the modulus of z isn't 0. Okay? So what does this give me? It gives me 1 minus the modulus of z squared divided by 1 plus the modulus of z squared. Or if I factor out a negative from the numerator, what do I get? I get negative times the modulus of z squared minus 1 divided by the modulus of z squared plus 1. Or negative x3. Okay? So what does all this say together? So x1 is fixed, and x2 and x3 negated. A rotation by pi radians in R3 about the x1 axis. Right? Let me use my right hand rule here. Right? My index finger points in the direction of x1. My middle finger points in the direction of x2, and my thumb points in the direction of x3. If I leave x1 fixed, i.e. point in the same direction, and rotate by pi radians, I flip the directions of x2 and x3, i.e. negate them. So, there's the algebra. You'll tell me by next Friday what the geometry is underlying this. Okay? Good. Okay, so great. This completes our study of the broad definition of complex functions of a complex variable. This is pretty much all there is to say when we're at that broad of a specification. Now what we want to do is impose additional conditions on such things so that we can build towards a concept of differentiability. And you'll remember from Calculus 1, depending on where you first saw it, what we have to do before we define a notion of differentiability is define a notion of what it means to take a limit, right? And then have to define what it means for a function to be continuous. And these notions coincide almost exactly for complex functions as they're defined for real functions. So again, in this development, as we move forward, and there's more and more similarity between what we did for real functions and what we can do for complex functions, it's a jarring surprise when we get to the notion of differentiability that it's so drastically different. Okay? So, bear with me. This might seem kind of boring for the next end of this day and beginning of Tuesday. And then we'll actually get to the definition of differentiability and be talking about something really interesting. Okay, but we have to trace through this development nonetheless. Okay, so the definition. A sequence of complex numbers which will denote Zn, where n is equal to 1, going all the way to infinity. Remember, a sequence is just a list of numbers, right? A real sequence, a complex sequence, whatever type of numbers we're considering, a sequence is just a list, as opposed to a series, which is a sum of possibly infinite terms, an infinite number of terms. But here we just have an infinite list. We're not doing any arithmetic operations among the elements of this list. Okay? So this sequence of complex numbers is said to have the limit Z0 or converge to Z0, we might also say. If for any positive real number epsilon, and this is a lowercase Greek letter epsilon, we usually use that to indicate something that's very small and positive. Okay? If for any real epsilon greater than 0, there exists an integer, capital N, such that the modulus of z sub little n minus z naught is less than epsilon for all little n greater than big N. Okay, so I know that notoriously concepts which involve epsilons and, as we'll soon see, deltas are confusing to students. And that's fine. We just need to take the time to really unpack what's going on here. Okay? What this is saying is that, okay, I have this ordered list of complex numbers. What this is saying is no matter how small I want the difference from this thing that they converge to and some members of this to be, no matter how small I want the difference to be, I can go out far enough, I can choose some positive integer n, so that I can take all the elements of this infinite sequence beyond n, and they'll be close to z sub naught. Okay? Let me draw you a little picture to accompany this. Okay, so let's say, here's my sequence. Here's Z1. Here's Z2. Here's Z3. Here's Z4. Z5, Z6, Z7, Z8, Z9, Z10, Z11, Z12, Z13, Z14, Z15. And then here, I have my point that I'm converging to, Z0. So I keep getting closer and closer and closer to this. So as far out as I go, I can choose a point where I chop off the initial segment of this sequence. I get rid of however many terms I want in the beginning. And I can always satisfy this, that all the terms of my sequence past a certain point will be in some neighborhood of radius epsilon. Okay? And it doesn't matter. See, I'm kind of like zigzagging here. I could even more wildly zigzag and still get to this point or converge to this point, Z naught. Because we're talking about a modulus. You just have to be in some neighborhood. Yeah.
Considering things like Z1 and Z2, it seems like Z2 is farther away than Z1 from Z naught.
Mm-hmm. That's true.
So, wouldn't that mean, if you're considering Z1 and Z2, that there would be an N greater than the big N? So if big N is 1, 2 would be farther away than epsilon? Then?
Right, so that is to say, for each epsilon, I can choose some large N. For each individual epsilon.
Okay.
Right? I'm not saying that for all epsilon that there's a single capital N.
Yeah.
I'm saying that for every epsilon, you can find, for each individual epsilon, you can find some integer capital N that depends on epsilon.
Okay. Yeah.
Okay, yeah, good question. Okay, so
It's kind of like saying that there is some Zn that is closer to Z naught than Z1, Z2, etc.
it's saying more than that. It's saying that every Zn
Yeah.
past a certain point is arbitrarily close to Z naught. Not just some Zn, but all of them afterward are progressively close. Okay?
Makes sense.
Yeah, good. Good. How are we doing on time? Oh, good, we still have some time. Okay, so, in this case, we write the limit as n goes to infinity of the sequence Zn is equal to Z naught, right? When this condition is satisfied. This is what we mean when we write this. Okay? Okay, so, this is a lot like what we do in calculus for functions, or, sequences of real numbers. Find the limit if it exists in the following examples. Let's look at A. First, the sequence, let's set Zn is equal to I divided by 3 raised to the n power. Okay? So, the key difference here is that when we look at sequences of real numbers, we're looking at the absolute value of the difference. Right? That is to say, there's only one way, or a pair of ways, to approach a limit. But here, as we were just saying, you can take any crazy path through the plane and get closer and closer to Z naught. Okay? So, that's why we take a modulus, so that we can actually compare. Remember, the complex numbers have no ordering. So we have to take a modulus to compare this to a real number. The closeness of successive terms of our sequence further out. Okay, so let's just note, what is the modulus of I divided by 3 raised to the n?
1/3 to the n?
Yeah, it's just 1/3 to the n. Okay, and now we can use what we know about limits infinity of 1 over 3 to the n is 0, right? We have the denominator growing as n increases, and the numerator is fixed. So we have to go to 0. So this implies the limit as n goes to infinity of the sequence I divided by 3 to the n is also 0. Okay? What the point I'm trying to make here is that to analyze sequences of complex numbers, we're actually looking at the modulus of the difference between the elements of the sequence and the thing we think it converges to. Right? I subtracted 0 here. Right? That is, z naught is equal to 0 in this case. Yeah. Okay. So let us look at the sequence. Zn is given by 2 plus I times n divided by 1 plus 3n. Okay. So let me re-express this in a slightly clever way. My standard trick, I'm going to multiply by 1 in a unconventional way, right? This is the same. The individual terms of my sequence can be written as follows. 2 plus in divided by 1 plus 3n times 1 over n divided by 1 over n. Right? I can do this because I'm letting n go to infinity. There's no risk of n becoming 0, right? Just by the way I define what a sequence is. N starts at 1. Okay? So, what do we get here? We get 2 over n plus I divided by 1 over n plus 3. So the limit as n approaches infinity here of 2 divided by n plus I divided by 1 divided by n plus 3. Well, again, I just use what I know from standard real limits, right? I take the limit of each summand separately, essentially. Right? So what's the limit of 2 over n as n goes to infinity?
9/3.
Yeah, right. So that's the total thing. The limit of 2 over n goes to 0, and the limit of 1 over n goes to 0. So we just get I over 3. Yeah. Or I thirds to be like this. That's a fun thing to say. Okay? Again, this is just familiar manipulation of limits, right? Okay. One more quick example. Let's let Zn be equal to I to the n. So, what happens here? Yeah, we just keep cycling through. Remember, I is a fourth root of unity, right? We have the terms of this sequence are Z1, Z2, Z3, Z4, Z5, Z6, point that we can choose. There's no any z0 that we choose, z0 that we choose. We cannot ensure that the further out terms of this sequence are within epsilon of any point z0 that we choose. Right? Because we'll always go this far away, this far away, this far away, this far away, successively. So we say the limit doesn't exist. Now, when we first talk about limits, calculus instructor to calculus instructor, this varies. Saying a limit doesn't exist is sometimes, according to some instructors of calculus 1 and 2, analogous to saying that the limit is infinite. Maybe, hopefully you guys haven't heard that before. It's not true, right? So here, notice that our modulus is bounded. Our modulus is always 1, but we don't converge anywhere. We don't converge to anything. So we say the limit doesn't exist. As you might guess, we can use the extended complex numbers to make sense of what it means to converge to infinity. Okay? And that's exactly what we'll do on Monday. So good. I'm glad to see you guys shocked by the claim that some instructors say that sometimes, but I've heard it before from students. So, good. So, yeah. Let's wrap it up there, and then we'll talk about continuity next Tuesday. And that won't take too long. Then we'll start to talk about analyticity. Yeah, so, I hope that everybody feels okay about the homework, but if you don't, I hope that you come to my office hours, because I don't think anybody's tried to come to my office hours yet. It'd be good to see some of you outside of class, if you so decide. Okay, have a good weekend.
Thank you.
Yeah.
Thank you.
Thank you. I pretty expressing, so I was trying to figure out how best to say it.
Okay.
So we had the definition of like the limit of the sequence is